Hello everyone, welcome to my second video. In the first episode, I installed Linux on my old laptop and started remote coding with Visual Studio Code. Today I'm going to create a Hello World server on Linux. After all, put everything on cloud is fashion now. Since I want to share data between computers before the first line of code, I took some time to understand what's happening on the internet and made a summary. I hope I understand all the network conceptions correctly. After that, I tried to understand C++ code that transfer data through sockets. As we all know, everything in the internet is identified with an IP address. If my computer wants to send some data to the server, she needs to know the IP of the server first. Like here, after I import the domain name google.com, the browser doesn't know the IP of Google server. She needs to ask DNS server what is Google's IP address. DNS server, which is domain name system, is the yellow book of the internet. Has records of all domain names and their IP address. You send them domain name and return IP address, and then you can access the website you want with IP address. The question is, what is the IP address of DNS server itself? DNS server, like a public service, we can always find some out there. In the old time, we need to explicitly configure it on the computer. Now, my laptop can get automatically as long as I have internet connection. Anyway, it's like a contact list in our phone. I want to call somebody, I have to find the phone number. I want to open a website, my computer has to know the IP address of this website. Let's see what's next after we got IP address. Here is the internet connection in my home. My computer's printer connects to the switch, and the switch is connecting to the router to the internet socket. Also, switch and router and Wi-Fi are in one box at my home. I think they should be working in the same way. Okay, I know the IP of my printer. Does the data can depart from my computer and fly to the printer now? The answer is no. We need to attach MAC address. What is MAC address? A MAC address is a series of hexadecimal digits assigned to network interface card, primarily specified as a unique identifier during device manufacturing, and as a physical address or hardware address. That is to say, my computer and my printer both have the network interface card, and each network interface card has a MAC address as its ID. Since the network interface card is the device who actually handles data in and out from network, only those data with which attached its MAC address is accepted. From my understanding, they are similar as send a mail. We need to assign recipient's name and address and the postcode on the envelope. The person who gets the mail can read the address to know if this mail is for them, and the postcode is for post officers to sort, distribute, and deliver mails to the destination. If we want, we can deliver the mail without a postcode. Also, in some types of network, device can communicate without IP address. However, just like postcode help us build a system which can efficiently deliver mails, IP address help us build the internet connecting the whole world. No matter how, we need a MAC address. Network interface card cannot read or does not care about IP address. The problem is, how does my computer know the MAC address of my printer? Basically, it's like my computer yelled to everyone in the room, "Hi, tell me your IP address and MAC address." After a while, my computer will know the printer's MAC address and any other devices who connected to the same switch, like the router. I think address resolution protocol supposedly to complete this job and create a match table inside the computer. You can check the table with ARP command. After the printer's MAC address is attached, the data can be deported. The data walk along the line to get to the switch. Besides the printer, the router also connected to the switch in order to correctly dispatch the data to the right destination. The switch also created a table match the MAC address and the specific port. Yes, switch yelled to every connected device. Tell me your MAC address. Then get the table. Okay, the data get in from port 1 and get out from port 2. When data arrives the printer's network interface card will check the MAC address, make sure the data is for her, and do the print job. Next, let's see how to send the data to the IP address we got from DNS server. First, my computer needs to know if the server is in the same local area network. The configuration called subnet mask can help. Subnet mask tells computer if the first 3 groups of digits in IP address are different, we are not in the same local area network. Imagine if I want to send a mail out of town, I should write the address and post code on the envelope, and send the envelope to the post office. I don't know how, but I believe the post officers would do the following jobs. In this way, server IP address was put in the data packet as destination IP address. But destination MAC address was set as the router's MAC address. Router here is called default gateway, which is another configuration you can check on your computer. When my computer finds an IP address out of town, she would just send the data to the default gateway, which I think like a post office. Fortunately, my computer already knows the MAC address of router. The switch also knows the router's MAC address and transfer data to the right port. The router in my home connecting to the internet and owns a public IP address, which I paid a lot of money. The configurations like subnet mask, default gateway, and public IP address, I do not have to set them explicitly anymore. Some protocols like DHCP would take care of them. I think the purpose of public IP address is, if anybody else wants to send me some data, they can find my address. Of course, I have to tell them my public IP address first. So, the router changed the source IP in the data packet to the public IP address, and the server could send back data I required to this public IP address, and also update the source MAC address and the destination MAC address, which represent the stuff for next step. I noticed that my router had 2 IP addresses. One is for my local network, and another one is for public internet. Actually, I think each port on the router has a MAC address and IP address, and every port connects to different network. Router will read the destination IP address and decide dispatch data to which port. This is a quite different big story. I'm not very clear, but MAC address is attached in every step as always. Okay, the server finally get my data and say hello back. On the way back, destination IP address and source IP address switched their place, and following the same rules, the data arrived at my router. But how could the router transfer the data to my computer? Remember before data left my router? Private IP was replaced by public IP. When router did that, my match table was created to log this visit. This table is called Network Address Translation Table. A port number was attached to public IP address to match different connections from my home. Like 1055 represents connection from my computer. 1056 represents connection from my phone. The port number will go with the IP address all the way to the server and returning back, so the router can track the port number in the returning data and replace it with original IP address and port number. Finally, the website I requested can be displayed on my computer. Actually, port number was adopted in most of network communications. When we have multiple apps access to internet, they have same IP address. Port number was introduced as actual identifier to assign data to specific apps. Like here, music player use 1322 and the chat app use port 1455. The well-known OSI model describes the functions of a networking system in 7 layers, each layer performing specific functions to enable communication between two devices or a network. Before the data was sent, port number, IP address, and a MAC address were added accordingly, and function in specific layer only care about a specific data header, like network layer only handle IP address. The model is very clear, however, in reality, seems sometimes beyond my understanding. In network layer, the data with IP address is called IP packet. The max size of an IP packet is more than 65,000 bytes. In data link layer, the data with MAC address is called frame. The max size of a frame is about 1500 bytes. Maybe the Wi-Fi frame is 2346 bytes. Anyway, it's less than IP packet size. So the IP packet needs to split into multi-frames. Every frame has a sequence number and can be reassembled after receiving. The layered mode means the above layer simply gives data to the below layer, doesn't even know how to implement the procedure. Like we deliver a package, we do not know the driver's name and the transportation they take. Let's do some coding. I'm losing my passion for reading more documents. Gemini told me socket is the first thing I need to know if I want to develop network program. There are two kinds of sockets which support TCP and UDP. Let's start with TCP. TCP stands for Transmission Control Protocol. It is a core protocol of the Internet Protocol Suite, responsible for providing reliable, ordered, and error-checked delivery of data packets over a network. I think, compared to the conception, it's more understandable what TCP is doing. TCP defines a couple of steps to establish the connection and terminate the connection. If client wants to connect with server, client sends a request to the server said, I want to connect. The server answers OK. Then the client returns, thanks, and I'm ready. Lastly, the server gets the message and connected. When either side wants to terminate the connection, just say, I'm gonna hang up. Another side also say, got it, I'm gonna have as well. Then the connection terminated. I think this looks like social rules or social norm. Random people can know how to gracefully interact to each other. IP protocol works in network layer. It is used to structure the network and the routing inside the network. TCP works in transport layer. Transmission Control Protocol. I think the name explains itself. IP helps you find the person. TCP tells you how to say hello. Totally makes sense. Okay, coding time. I asked Google Gemini to show me some code about the socket communication on Linux, and copied the code to Visual Studio Code. I don't understand most of the lines of the code, but it's working. These codes are running on Linux on my old laptop. I'm programming remotely. To make it easier, I downloaded a TCP terminal as client to send message to server. TCP terminal is running on Windows locally. The IP address here is my old laptop. Step 1. Establish the connection. Step 2. Send message. You can see the server gets the message. With the help of ChatGPT, I roughly understand how the code works. Step 1. Create a socket object. The arguments assigned the protocols are IPv4 and TCP. Step 2. Specify the IP address and port. Step 3. Bind the address to the socket. Step 4. Start listening for the connection. The program will stop here until get a connection from client. So step 5. Accept connection. Looks like after accepted the connection, a new socket object was created. The program stops again to wait the client send a message. And then, step 6, receive data. At the end, don't forget to close everything. There are many details I'm not very clear. My primary concern is the buffer size. In this case, I just allocated the buffer as 128 bytes. This is a very small buffer, and I'll send a huge message to the server and see what will happen. I copied a long text from somewhere and connect to the server and send. Looks like the server only received the first little part of the text. I believe this is because the small buffer I allocated. Let's make the buffer 10 times bigger. Do we get 10 times longer text? I'm not sure. However, I don't think this is the point. There's no way we can set the buffer big enough to receive all the text at one time. The server should keep receiving until the end of text. Okay, add a while loop over receive function. Should get what we want. Don't remember clear the buffer before receive function. Looks like we successfully sent the hello text to the server. And we can continue send the message. If the client terminates the connection, receive function will return 0. The other conception I cannot understand well, even with the help of ChatGPT, is blocking mode and non-blocking mode of socket. I remember in JavaScript, asynchronous task is very common. You tell somebody to do something and he will call you back when he's done. Maybe implement non-block mode is the first step to do that. Add this code segment could set the socket working at non-blocking mode. Let's see what it is. The program didn't wait for the connection, directly running to the end of the code. You need to add a while loop to make it better. In every loop, run accept function. If get no connection, set for 1 second and continue the loop. This is non-blocking mode. After get the connection, go to the receive function, ready for message. But it looks like the receive function still in blocking mode. ChatGPT cannot tell me how to set the receive function at non-blocking mode. After Googling for a while, assign the last argument of receive function, as the message "don't wait" could help. In every loop, if got no message, sleep 1 second and continue the loop. OK, the receive function is in non-blocking mode as well. If we terminate the connection on client side, the server will go back to wait connection loop. Wait for next connection from client.